guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So here's a limiting reactant problem. Calcium carbide, which is written as CaC2, reacts with water to form calcium hydroxide and ethine, which is C2H2. Okay, so they're asking you what is the limiting reactant when 1 times 10 to the power of 2 grams of water reacts with 1 times 10 to the power of 2 grams of the calcium carbide. So what's the first step that we went over before? It's balance the reaction. Okay, so let's balance this. We have CaC2 plus H2O, CaOH2 plus C2H2. So we have 1 calcium here, 1 calcium here, wonderful. We have 2 carbons here, 2 carbons here, great. But we have 2 hydrogens here, and we have 4 on this side. So what do we have to do? We put the 2 right here. And then by doing so, we actually balanced out the 2 oxygens on both sides. So that was a really simple balancing. Okay, so now we want to calculate the molar mass of the reactants. So for the calcium carbide and the water. So step 2, the molar mass of calcium carbide is 64.10 grams per mole, which you can find from the periodic table. For water, it is 18.02 grams per mole. So from here, we need to calculate the number of moles of each of the reactants. So that's really straightforward too, right? Because we know the grams and we have the molar mass. So 100 grams divided by 64.10 grams per mole gives us 1.56 moles of calcium carbide. And for here we have, again, 100 grams divided by 18.02 grams per mole. And we end up with 5.55 moles. So now let's compare the calculated moles to the required moles. So what that means is for every 1.56 moles of the calcium carbide, that requires 2 times 1.56 moles, or 3.12 moles of H2O. And the reason for that is we have 1 mole of calcium carbide, but we have 2 moles of water, right? So for every 1.56 moles of calcium carbide, we are going to have to need 3.12 moles of water. But since there are 5.55 moles of water available, that guy's in excess. Excess, if I can spell that. Okay, so if water is in excess, what's the limiting reactant? This guy, which I'm just going to write as Lr. So now, by calculating the moles of each of the reactants, we were able to find out which guy was in excess and which guy in turn was the limiting reactant. So now that you guys were able to do a limiting reactant problem, now I wanted to jump in with a theoretical and actual yield calculation. So the theoretical yield is the maximum amount of product which can be produced in an ideal world. So in the real world, it's actually really difficult to produce the same amount as obtained for the theoretical yield. So what this means is based on the number of moles of the reactants, you expect C to be a certain value, X number of moles. But due to experimentation, due to errors, basically in our world, we are unable to achieve this perfect theoretical or estimated yield for the amount that we start out with. So from the value of the theoretical yield and what you actually obtain from experimentation, you can calculate the percentage yield, which also gives you a really good indication of how accurate your experiment was. How much did you actually get of what you were expected to get? So this is written as the actual yield over the theoretical yield times 100%. And now I'm going to show you guys a problem that actually involves a percentage yield calculation at the end, so I can walk you through a full limiting reactant problem.